Okay, so thank you very much. We are open for questions. Okay, sorry. Oh.
So you show plots for very low masses like 0.5 GeV, 1 GeV, but is this effect still there for higher masses? And if yes, it's irrelevant compared to the other usual methods or not?
So the xenon limits are probably this blue one, I think. So I showed from 1 GeV and below. So there should be a smooth transition below 1 GeV onto the standard limit. So it gets more complicated because you have to take into account you have an electron which has some energy and you have a nucleus which has some energy. And you have them all both inside the detector. And that's more challenging. But principally you can do it. But you always have the suppression effect. So you'll expect it to sort of come down and then smoothly match on. But it's not. But once you get up into this higher range, then just the ordinary thing dominates.
Here a question. When you talk about the signal in the electronic recoil region and the nuclear recoil region, can we go to the plot? So from here, I'm getting that it doesn't have like a specific signature. It's like it could be either in the region of nuclear recoil or electronic recoil. How is that? How does it make it appealing for experimentalists to try to look for this signal?
So the signal lies here, which is it is an electronic recoil signal, but it lies also over the nuclear recoil band where your signal should be lower. So you're not going to have background in here.
But for example, how is this different from I don't know an Auger electron from excited xenon molecule? Is the
So you can it's a part of your background. So you might worry about say argon 37. They have a decay of like a kV electron. So you should have some background in here from this bond.
Okay.
That's true. Every dark matter.
Okay, thank you.
So going back to the question about higher mass dark matter, and you mentioned this kind of dual signature of an electron plus a nuclear recoil. Does that mean that our model for a pure nuclear recoil is wrong, or is the rate also sufficiently low for higher masses that we can ignore it?
So if it goes wrong, it goes wrong. So I don't know how you did your nuclear recoil calibration. If you use like a DD generator like Lux did, the energies that they use are above where this effect has become important.
But for the dark matter. So it doesn't affect the neutrons, but does it affect the dark matter potentially?
Not at high mass. So it's a suppressed contribution.
It's sufficiently suppressed also at high mass.
One more question.
It's completely unrelated to this talk. So since in some previous talk it has been mentioned the directionality or the dependence on velocity and directionality of dark matter, would you comment about how do you expect any limit that we've seen to change if we have a non-thermal component of on the top of the halo, or what happen if you have like a high velocity or low velocity stream or something like that?
It is for the signal.
Anything you want to address.
Well, so I don't know what Fabio is asking me. Last year I did have a paper about called the dark matter hurricane, so a high velocity component of dark matter, so stream dark matter coming towards the Earth with a speed of about 500, 600 kilometers per second. And I've been at this workshop. I've been wondering, does this actually change the spectrum in any way? So we've got this, say, 10% component of dark matter, which is not coming 300 kilometers per second, but it's coming 600 kilometers per second, what we might have. I don't think it is going to change the signal much, but I should actually do the calculation and check. So that's a good idea. Was that your question?
Okay, so I think we can thank Christopher again. Thank you. Okay, so the next speaker and the last speaker of our morning session is Francesco Deramo from the University of Padova and INFN.
Okay. Good morning, everybody. And first of all, of course, thank you very much to the organizers for inviting me here. It's my first time in São Paulo, my first time in Brazil, my first time below the equator as well. So it's a very exciting week. I will be here for a month, staying at the USP. I also learned that I have to say USP. So I'm really looking forward to this month here. Today, I will tell you about some work I've been doing in the last few years, roughly 4 or 5 years. And the work is about developing new theory tools to interpret the results of dark matter searches. And it's very nice that I was put at the end of this morning session, because even though the tools I will present will apply to all dark matter searches, the original motivation for this research was direct detection data. Okay, so I would like to start from this plot that we have already seen a few times this morning, and I think the motivation for this type of tools is even stronger today than a few years ago when I started working on this, because in the last few years the limits got better. And here there is our current best limits for the dark matter direct detection cross-section in the so-called WIMP mass range. So we also heard this morning about the sub-GeV region. We heard the talk before mine as well. But for this talk, I would like to focus mostly on the WIMP mass region, which is roughly between 1 GeV and a few TeV. And this black line is our current limits. So when a theorist like me looks at this plot, the question we ask ourselves and we would like to understand is, okay, so you're giving me bounds on the mass versus the cross-section, but from the microscopic point of view, from the particle physics models of dark matter, what do we learn from this plot? Okay, so let's look at a couple of benchmarks. WIMPs were suggested in the 70s, and the W of WIMP stands for weakly. And at that time, weakly was really weakly in the sense of weak interactions. So a typical WIMP candidate was some new degrees of freedom charge under the weak interactions of the standard model, for example, like a 4th generation neutrino, so a particle exactly like the neutrino, but with a much higher mass, a mass in this range. And the cross-section for this type of candidate is here, where this is I hope I did the math right. So you see, this is 10 to the minus 43. The cross-section is 10 to the minus 39. So it's badly excluded. We knew this for a long time, but just as a reference. The region we are probing now, which is roughly this region, is the cross-section you expect in a model where interactions between dark matter and boson of the standard model. Of course, there is some model dependent because we don't know the coupling of the dark matter to the Higgs boson. We know the coupling of the standard model particles to the Higgs boson, but there is every parameter, but roughly we are currently probing and excluding this region. Okay? So there is some concern when you look at a plot like this, because especially after you impose Rayleigh density constraints. Okay, so you want that the couplings you are probing here are such that they are also able to give you the right Rayleigh density in the early universe. So these Rayleigh density calculations have caveats we can discuss about, but they are useful benchmarks. And it seems very difficult to reconcile Rayleigh density and direct detection bounds. Okay, typically, when you want to reproduce the observed abundance, you end up above this black line. Typically, okay? Then we can discuss about the single details. So we are facing a situation where the limits are stronger and stronger with time. They were already concerning a few years ago when I started work on this. And it seems natural, at least to me, that if the dark matter lives in this region, okay, of parameter space. So cross-section below the limit, and let's say above the neutrino floor, even though we heard this morning one possibility to overcome this barrier. It seems natural that there is a price to pay in the rate, in the sense that this rate, the cross-section is small because of a good reason to be small, not just because we put it small by hand. Okay? So let me show you a couple of examples. A natural example is the so-called leptophilic dark matter. So these are dark matter models where the dark matter talks only to leptons of the standard model. So electrons, muons, taus, okay? And of course, if you do a calculation at 3 level, you don't find any signal because we are computing a nuclear recoil. But then if you go to higher order in perturbation theory, for example, computing this loop diagram, then you find the cross-section that is 1 loop below the one you would expect. So this is a reason to justify why the mass is small. And the Rayleigh density can be set by coupling to leptons. So there is no tension between Rayleigh density and the indirect detection cross-section. So this is one example. Another example is when you do a calculation at leading order, 3 level, you have some type of coupling which is spin dependent. Okay, so it doesn't have the coherence enhancement of a square, the number of nucleons square. Then you go to higher order in perturbation theory, you compute 1 loop diagram, and you end up having a spin-independent coupling, loop suppressed. But the spin-independent coupling has an enhancement of a square, where a is a big number, is 200s, more or less. So you get the 10 to the 4 enhancement, and it's worth paying the price of a loop. So you go to higher order in perturbation theory, but you win in the rate because you generate a coupling which is enhanced by the nucleus. Okay, so this is the spirit, and this example I put the references, and these are just 2 examples. There are many others, just for illustrations. These were known a few years ago. What we tried to do was to do a systematic study of these cases. Okay, so there were examples known, but we tried to be systematic in the analysis. And so, as I said, there are many others. So these are the references of the work we've been doing in the last few years. And as I say, the goal was to be systematic, but the goal actually was twofold. On one hand, it was to go through these cases in a systematic way, not just by providing examples, and this requires new development of theory tools and new calculations, okay? But then also we wanted to provide the community with the tools in such a way that the inclusion of these effects is automatic for the use, for a model builder that is studying a dark matter model and he wants to know if this model is excluded or not without doing the calculation again, okay? And so we did both. And I mentioned that the study was motivated by the tension between direct detection data with other probes of dark matter couplings, and that's why we started doing this. But the actual final output turned out to be more useful than just direct detection data. It was useful for all the other experiments. So instead of following the chronological order, let me just give you a broad overview of the different dark matter searches and why this approach was useful. Okay, so we know that WIMP dark matter searches, there are different kind, and by different kind that do not only mean different experiments looking for the same type of process. This morning we heard about several direct detection experiments, but they always look for non-relativistic elastic scattering of dark matter particles, okay? But we know there are also experiments such as indirect detection, such as collider, where they probe something completely different, a completely different process, and the process happens at a different energy scale, okay? So by studying nature, by looking at the visible universe, at the standard model, we know that the coupling of each particle are scale dependent. The most famous example is the running of the strong coupling constant. So we know that strong interactions get weaker as we go high in energy, okay? Dark matter is no exception. Of course, we still don't know the theory, so we can only do calculation for some given theory, but dark matter couplings at different energy scales are different. Okay, so here when you do direct searches, you are probing very non-relativistic physics. So the energy scale you are probing is GeV, let's say, the scale of the nucleons, where you have the effective theory with nucleons. Same for the indirect detection experiments, where you search for dark matter annihilation. The center of mass energy is set by the dark matter mass. Okay, so these are non-relativistic annihilations. So you are really probing couplings of dark matter at an energy scale equal to twice its mass, just because you have two of them in the initial state. Finally, for collider, you are looking at dark matter production, and you are probing couplings of dark matter at an energy scale set by the center of mass of the collider. So we have different colliders, but it's much higher typically than the other ones. Of course, you can have, so this is fixed, for example, for the LHC. The indirect detection scale is changing with the mass. So if you probe dark matter of UTV, you are probing here. But for each model, once you specify the mass, you can do that. So the theory tools we wanted to develop, and that we actually develop, they can be summarized in these two items. The first one is the language we used. So we use the language of effective field theory, which are just established quantum field theory techniques to describe a physical system at the given scale, at energy scale, by only specifying the relevant degrees of freedom. For example, the Lagrangian that Fermi wrote to describe the neutron decay, we know now that this is a process mediated by the W boson of the Standard Model. But at that time, nobody knew about the W, and it was not relevant because the energy scale involved in the game are much, much smaller than the W mass. So this is the language we use. Of course, we wrote down a theory analogous to the one that Fermi wrote from the Standard Model. And the tool we use to connect the different energy scale is renormalization group, which, again, are very established techniques, widely applied in other fields of particle physics, such as flavor physics, when you want to evolve the coupling of B mesons. And this is a mathematical tool to connect couplings of a given theory at different scales. Okay? So within this language now, let's go back to the original motivation. Imagine you have a theory that at high scale couples the dark matter only to the top quark. Okay? There are theories of top philic dark matter. The other one was leptophilic. So I'm saying the top just because you don't expect a significant rate in the direct detection experiment because there is no top in the nucleus. Now, this is a statement that you make at high scale, where you write down the theory. You evolve the couplings at low scale, and you induce through this renormalization that, in practice, what you do, you compute higher order correction to the couplings, similar to the loops diagrams I show in the second slide. You induce these couplings here to light quarks, up, down, and strange, or to gluons, so something that you can, or photons, something that you can probe in direct detection, and then you end up having a rate that you can probe. Okay? This is just one example. And I would like to emphasize that the inclusion of these effects is not optional, in the sense that all you are assuming when you do this calculation is that the standard model of particle physics exists. Okay? So once you write down your theory of dark matter, all the corrections you include are with standard model particles in the diagram. So these effects can be small, can be large, depends on the case, but in principle, they have to be included. Okay, so now let me tell you a couple of more words about the general framework, then I will show you results. So the framework we built, it's something very analogous to the effective theory of weak interaction that I mentioned before, that Fermi wrote in the 30s. So we assume that the dark matter particle is the only new particle experimentally accessible, which is typically a good assumption in direct detection experiments, unless you have some very light mediator. And so from the Feynman diagram point of view, you're just collapsing the propagator of the mediator to a point, exactly like the theory for weak interactions. So this could be a W or a Z. And the effective interaction of dark matter fields chi with the standard model quarks are parameterized by contact interactions. Okay? So we classify these contact interactions in a model-independent way because these contact interactions parameterize all possible theories at high scale that gives you this low energy effective interaction. We do that for a standard model fermion dark matter. So you see this is the Dirac Lagrangian. And we classify all possible effective interactions, classifying them by the mass dimension of the operator. So in the standard model, weak interaction, this would be a dimension 6 operator suppressed by the mass of the W square. Here we just put a generic lambda because we don't know the mass of the mediator, but we just classify systematically all possible interactions because I said at the beginning we wanted to be systematic in this classification. So these are the operators at dimension 5 and at dimension 6, where chi is the dark matter. So, but don't worry about the details, just to tell you that we got all the operators. So we classified all of them, and we computed all loop diagrams like these ones that I sketch here in the figure. The output of these calculations are differential equations where the variables are the couplings of dark matter, and the variable, so the coupling as a function of the energy scale mu. So these are a set, this is just a schematic notation, but a set of coupled differential equations where the variables are the coupling of dark matters, and these equations describe the way they evolve with the energy. Okay, so this achieved the first goal of classifying all the possible interaction and describe how they evolve with the energy. As I said, we also wanted to make the inclusion of these effects easy for the community. So we also release a public code that we call RunDM, because running is the jargon to call the evolution of the coupling with the energy scale. We say the coupling runs with the energy scale, and this is if you are interested, we can discuss more about the code offline, but it just takes as an input the couplings at the given energy scale, and it gives you as an output couplings at a second energy scale that you can choose, or if you want, you can make the one at the direct detection scale. Okay, so since I have only 4 minutes left, okay, so let me just say that the inclusion of these effects was applied, and so this code, which was in turn based on the calculation, was applied by ourselves to study cases where the bound of the dark matter as a function of the mediator mass from direct detection experiments is substantially affected once you include these corrections. So there are cases where the inclusion of the correction completely changes the conclusion about what is allowed and what is not. It was also applied to indirect detection spectra. So in this paper from last year, we studied models of leptophilic dark matter, and we show that in indirect detection, you expect, for example, antiprotons for leptophilic dark matter. And this is only possible if you consider corrections, because you only annihilate 2 leptons. Okay? And there are many other applications. So in the last 2 minutes, I would like to mention 2 things. The first one is that we were very happy that we were not the only one using our code, but this code was used by a bunch of collaborations of people that studied dark matter models, and they employed our results to check if their model was allowed or not. And I mentioned this paper not only because it was written here by Enrico, Giovanni, and other people, but also because it was interesting that although our original motivation was to study the WIMP mass region, they realized that our results are actually valid also in the sub-GV mass region. And so they exploit the complementarity of different searches for these candidates, and they connect the different energy scales involved by using our code. And since our calculation now, there is a new competitor collaborations, which of course is very good because it motivates everybody to do things better. They improved slightly our calculation by going to dimension 7. We stop at dimension 6. And they also consider dark matter charge under some model gauge group. And they also release another code that does more or less the same. We can discuss about the details. And finally, this is my last slides. We are working on updating our results, and we are also planning to release an update of the code. And we put up, I put up this collaboration funded by some University of Padova grant, and I even hired Enrico yesterday, so we also have a connection in Brazil here. And the goal, the broad goal is to improve our, again, the effort is always twofold. The first one is to develop the tools, and so to do calculations and find results, and the other one is to release a tool that can be used by the community. So we are planning to extend the calculation on a bunch of directions, but most importantly, both our code and the competing code, they only evolve the coupling. So if you tell the code the coupling at some scale, it gives you the result at a different scale. What we are trying to do now is to develop an improved code that will also show recoil spectra for different detectors for each model you choose, and also that it computes the exclusion bounds for you. So the life of anybody using this code will get easier. Okay, so I will stop here and I will leave my conclusion on the last slide. Thank you.
Thank you very much, Francesco. We are open for questions.
So Francesco, in the paper you wrote with Punchy, where
Which
you
one?
have for the indirect detection.
There's two.
Yeah, so the one, could you go back? The one, yeah.
This one?
The one with indirect detection.
Yeah, indirect, sorry, yes, this one.
Yeah, this one. So how is that different from the electron for beam slalom that we've done before?
Good. Okay, so I was a bit fast here. If the dark matter mass is above the Z mass, then you can annihilate to Z bosons or W bosons, and then they will shower and they will give you antiprotons. So even if you are, sorry, not annihilate. So if you are leptophilic, you have a mass very high. You annihilate to leptons. The leptons radiate Ws or Z, and then you have antiprotons. What we show is something different. We consider masses below the Z mass. And so it's a new effect, different. So you, so no, so I was, so I, oh, where is that?
Yeah,
here.
that one, yeah.
No, so I was saying that this was known and it was pointed out for the first time in this paper.
I see.
So what we did was to consider lower mass and
yeah, there you can see.
and then show that you get antiprotons also in this mass region after you include these corrections.
Okay.
So just a comment on this question, actually, as a cosmic ray physicist, I'm very interested in the room left for leptophilic dark matter. So in the light of your talk, do you have some...
So hopes? You mean the access... So the access is, I think the most relevant comment about that access is about this, not only this paper, this was, I think, the first one who mentioned the effect. If you want to reproduce the Pamela, AMS, and Attic, Fermi, all of these positron access, you need a very high mass. And at this high mass, you produce antiprotons because of what we were just discussing. And as far as I know, you would produce too many. And so I think it's not consistent to have some leptophilic dark matter explaining the access at the same time consistent with the antiproton bounds.
So even the leptophilic dark matter would produce you an antiproton flux that is not compatible with AMS
above what you see. It's above what you see.
Have you checked that in your paper?
Not us, because this was already known. It was studied by other people. So
but you have updated measurements. Anyway, I will ask you later. Okay. More questions.
Can you go back to the direct detection? I think slide before this one.
This one?
Yeah. This
sorry, I was a bit fast.
So you went a bit fast there. So I just wanted to. So you emphasized the effect of the running.
Yes.
I thought, and you mentioned this plot that there was a big change. I wonder if you can explain. So we haven't measured those couplings either at high scale or anything, right? So this is happening at low scale. But so what is this? Why do you get a difference? I mean,
okay, so I can give you more details. So this is a theory where you have a current-current interaction. The dark matter has a vector interaction, and the standard model has an axial. And I'm taking now a model where you have a z prime, okay, a spin 1, giving this effect. So something else we did was to compare these results with bounds from the LAC, okay? So before our study, you found statement in the literature saying that direct detection experiments cannot test this type of theory because this cross-section is spin-dependent and velocity suppressed. So the only hope you have is LAC. We checked that after including these effects, direct detection limits are much better than LAC.
Can I ask you the difference between run DM and direct DM? So in the other,
so
direct DM does what?
I'm trying to understand because it's from 1 year ago, but it's recent. So being very honest with you, where is the slide? Sorry, here. The type of calculations they did is it's more extended than ours. So they consider more cases than the ones contemplated in our code. So they went to dimension 7. They also consider dark matter charge under SU2, the standard model. So from this point of view, they do more. But if I understand correctly, their code is only for direct detection. So there is no freedom to choose the scale, and you can never produce, I think, plots like this, where for indirect detection, it's really important to have the freedom to evolve the way you want.
But do you do the mixing with the pions and the etas?
The pion?
No, well, they go from 2 GeV down through the QCD phase transition. So they have pion and eta mixing as well.
Yeah, but this, yes. So this is, you mean the matching from quark and gluons to nucleons? Yeah, so this is only relevant for dimension 7 operators. It's not? I mean, for vector currents, it's, for the axial, you mean? For the axial. Well, in our code doesn't do the matching. Okay, so direct DM, I'm not sure. I don't remember exactly what I do. Our code doesn't do the matching. The output of our code is coupling to quark and gluons at the GeV scale. And then you can use, yeah, they also have an update about this matching.
Okay, thank you very much again.
Thank you.
Okay, so the session is over. However, hold on a second. Enrico has an announcement.
Yes, so I would just urge the speakers of this afternoon either to give me or to send me the talks so that I can already put them in the laptop before the session starts, please.
And for tonight. For tonight. So just before we go for lunch, we would like to, tonight is the social dinner. That means that we organize it, but we cannot support it. So we will have to pay for yourself. Sorry about it. It's gonna take place in a pizza place, which is very traditional in Sao Paulo, as a matter of fact, because there was a huge Italian immigration, as in Buenos Aires, but in Buenos Aires from the south, in Sao Paulo is from the north. And you cannot, can you hear me? Okay, so it's gonna be a pizza place, so it's also easy to arrange for vegetarian option, just in case you have meat problems. And it's gonna be there. We would like to ask you to be there by 7:45-ish at the latest, because otherwise they will not keep our reservation. And I guess we'll start eating by 8, so at the time that people collapse there by 7:45. And but tonight we have something here from 5 to 7, which is in the program. And be there. The reservation is named Fabio. We will go from here. It's either the yellow line, Faria Lima, it's the station is this one. It's either a walking distance from Faria Lima, which is on the yellow line, or you take a Uber and that takes you there. So see you there and see you in this afternoon at 2 p.m. Have a good meal.